Let's talk about cosmic strings, infinitely thin, immensely dense threads that run through the entire universe and carry scars from its birth. Do they exist, or are they pure myth? What do we mean when we say a theory is wrong? This question has been keeping me up at night. There are two answers to this question. The first answer is no. The second answer is not yet. Let's try to figure out how we got from no to not yet. At time zero, our universe was born in the Big Bang, an unimaginably hot, unimaginably dense singularity. Almost immediately, though, it started to expand and cool. As it did, different types of matter condensed just like water vapor condenses into dew on a cool morning. But unlike water vapor, which condenses into tiny droplets, the stuff of the universe condensed into all possible size ranges, everything from planets to stars to black holes. These phase transitions, rapid changes in the state of matter, left behind some weird topological defects, and those are the cosmic strings. Let's go back to the water analogy. Imagine pouring hot water into a pan on the stove. The water at the bottom cools down faster than the water at the top, so the water at the top tries to flow down to the bottom to even out the temperature difference. But by the time the top water gets to the bottom water has cooled down even more, so the top water now has a net flow to the left. And since the water at the top isn't instantaneously communicating with itself, some of the water ends up flowing uphill. You get these kinks in the interface between the hot and cold water that remain locked in place because the water can't unmix. Cosmic strings are kind of like those kinks in spacetime. Now, since these strings are theorized to have formed at the beginning of the universe, they should cut right through the Earth, the Sun, the Milky Way, and all of spacetime itself. If they are real, and if they are big enough, then they should affect gravity and light in a way that we can detect. So how big are we talking about? Well, the diameter of a cosmic string is supposed to be about 10 to the negative 33 centimeters, or about 10 trillion times smaller than a proton. So how do such thin threads affect spacetime? The answer is they don't really. They only become important when they move, and that's what we're looking for. We're looking for movement. Because of the way they're created, these strings would have immense tension along their length. Imagine squeezing a slinky and then letting go. Once you let go, the slinky oscillates back and forth. That's what the universe would be like if it had cosmic strings. It would be filled with ripples in spacetime, called gravitational radiation. And although we haven't detected them yet, there are several paths we can take to find evidence for their existence. The first path leads us to distant galaxies. According to Einstein's theory of general relativity, massive objects warp the space around them, bending the paths of light rays that pass nearby. This warping of space is what we call a gravitational field. When light passes through a region of warped space, its path bends. This bending acts like a lens, magnifying and distorting the images of objects located behind that massive object. This is called gravitational lensing. And while gravitational lensing doesn't usually cause double images, there is a rare case where it does. If you have two galaxies that are close together and have roughly the same mass, the space between them will be completely empty. Light passing through that empty space won't be bent, but the light from each galaxy will be bent toward you by the mass of its own galaxy. The result is two images of the same galaxy. And while we've seen a few examples of double-image galaxies, astronomers have ruled out the most likely explanation, that the two galaxies are just really close to each other. There are no galaxies between us and the doppelgangers. In fact, the galaxies are separated by vast distances. And the only explanation for this is a cosmic string. Another path leads us to pulsars. A pulsar is a highly magnetized rotating neutron star that blasts particles out of its poles like a cosmic lighthouse. The particle beams sweep across space, reaching Earth every time they complete a rotation. Astronomers use these pulsars as cosmic clocks, measuring the time between pulses to better understand the universe. Pulsar timing arrays measure the effects of gravitational waves on these pulses, just like cosmic strings. Gravitational waves stretch and squeeze space, changing the distance light travels between pulsars and Earth. Scientists analyze the timing of these signals to infer whether or not gravitational waves are stretching them. It's actually possible that cosmic strings would produce a special type of gravitational wave called a string cusp. Cusps have a characteristic chirp to them as the frequency increases with time. This chirp comes from the fact that the strings are infinitely thin, so their ends curl up into themselves. These cusps will eventually be detectable by pulsar timing arrays, and there's already some hints of an anomaly in the data. However, before you start worrying too much, scientists have already ruled out a number of other potential sources of the signal. So while there's some evidence, it's still not quite cosmic strings. A third path to evidence is through the cosmic microwave background. The cosmic microwave background is a remnant of the Big Bang. It's the oldest light in the universe, and it's stretched by the expansion of the universe until it falls into the microwave part of the spectrum. While the CMB is incredibly useful for understanding the early universe, it also has some drawbacks. Namely, it's really hard to detect features smaller than 1 degree across. That's because the whole universe is like 120 degrees wide, and anything smaller than 1 degree is drowned out by the overall signal. It's kind of like trying to listen to someone speak in a crowded room. All you hear is just noise. But cosmic strings should leave behind a very unique signature in the CMB, a faint ring of light around the ends. That's because as the cosmic string moves, it drags spacetime with it. That dragging effect creates a sort of wake that stretches out behind it like the bow wave of a boat. Now, scientists have searched for this signature in the CMB, and there's some potential evidence, but nothing conclusive. So let's summarize the evidence. First, we have gravitational lensing. While there are some anomalies that cannot be explained by standard gravitational lensing, they could be explained by other things. We also have gravitational waves. There are some hints in the data, but they could come from something else. Then we have the CMB. There are some potential rings, but they're too faint to tell for sure. All right, so we haven't found any evidence for cosmic strings, but that doesn't mean they're not out there. Remember, I said the second answer to the question is not yet. But why? Isn't it just that we haven't looked hard enough? Well, yes, but also no. One thing you have to keep in mind is that if cosmic strings were never created in the first place, then you can look forever, and you're never going to find them. So really the question we should be asking is, given the current data, how do we put limits on the properties of cosmic strings? For example, given the current data, we know that the total length of all cosmic strings together can't be longer than 10 raised to the 17th meters, or about 10 billion kilometers. And that's a lot of string. It's also possible that cosmic strings could form closed loops, but the constraints are much tighter for loops. The combined length of all cosmic string loops can't be longer than 10 raised to the 10th meters, or about 10 million kilometers. So yeah, we haven't found any evidence for cosmic strings, but we haven't exactly found evidence against them either. Some of the anomalies we talked about could be explained by cosmic strings, but they could also be explained by something else. As Carl Sagan once said, extraordinary claims require extraordinary evidence. We don't have that evidence yet, but we're looking. So what would you see if a cosmic string passed between you and a galaxy? A. A perfect ring. B. 2 offset twins. Or C. A smeared arc? Pause the video here if you want to make a guess. In any case, the answer is C. A smeared arc. Here's why. For simplicity, let's assume that the string is infinitely thin, doesn't move, and is straight. If we imagine an observer on the string, they would see the galaxy appear as a ring, because all points of the galaxy would be the same angular distance away from the observer. Since the string is infinitely thin, we would expect the gravitational field of the string to be negligible compared to the galaxy. So the shape of the galaxy would not change, but the angular size of the galaxy would increase as it approached the observer. If we then imagine moving along the string, the angular size of the galaxy would slowly decrease until it reached a minimum value, when the observer was directly between the galaxy and the midpoint of the string. At this point, half of the galaxy would be in front of the string and half of the galaxy would be behind the string. From this point, the angular size of the galaxy would increase again, but now the galaxy would appear to be offset from its actual position. If we then continued to move along the string, the offset would grow until it reached a maximum value when the observer was halfway between the galaxy and the end of the string. At this point, the observer would see the full extent of the galaxy, plus a bit more because of the way the gravitational field of the string warps space. The warping is so subtle, though, that it wouldn't be noticeable unless you were paying close attention. After passing the end of the string, the apparent size of the galaxy would decrease until the observer reached the end of the string. At this point, the galaxy would disappear from view because the string would block the line of sight. Then the whole process would repeat itself as the observer moved further along the string. So what do you think? Was this video helpful? Let me know in the comments below. And if you want deeper dives into frontier cosmology, subscribe and ring the bell. We'll chase the edges of reality together. Some models predict networks of strings hidden across the cosmos. If one zipped through our solar system, its tidal effect could outmuscle planets, yet it might be thinner than an atom.